Okay, so our next speaker is Hongye Yu. So please take it away.
Hello everyone, I'm Hongye Yu from Stony Brook University, and I'm going to present this ongoing work together with BNL and QERA teams on this maximum independent set problem of classically hard instances. So, So unlike many of the talks today, our problem here is a purely classical problem. So the maximum independent set is defined on a graph where we have vertices and edges, and a independent set is defined as a subset of vertices that no two of them have any edges that connect to them, and the maximum independent set is just the maximum of independent set, which is the independent set with maximum cardinality. For example, for the graph listed at the right side, so the MF is simply these two solutions, 1, 3 or 1, 4. So the problem itself is very well studied in classical context, and it is NP hard in general, and which means for a generally speaking, the problem is extremely hard to solve in classical computers. And we will look at the problem in quantum aspects and to see if we can find any quantum improvements on that. So before that, I will briefly introduce the problem and its hardness from the classical side, just for let us get some grasp of how hard it is and where the hardness comes from. So MS itself is a very common problem in real world problems such as like social media or transportation systems, and it is NP hard, and it's also a famous example that it is hard to approximate, which means it is hard to find the exact maximum independent set. It is also very hard to find an approximate maximum independent set, which means if you want to find a independent set with size that is close to maximum, it is still very hard. And why should we study this hard problem and on QERA's machine? So the advantage is the QERA Rydberg atom machine contains a naturally repulsive potential for two Rydberg atoms. So if two vertices they present nearby, then there would be a very large repulsive potential, which is this Vij term. And this will increase the energy by a very large amount so that we can naturally distinguish from the independent sets and non-independent sets from the hardware side. So, and the classical on the classical side, the best algorithm for general graph, which means the every two vertices can have edges no matter how far their distance is. And for such graph, the best algorithm in classical computer is called the branch and bound, and it requires exponentially long time to find the exact optimum. And what if we lower our goal a little bit? We don't intend to find the exact maximum, but find that graph independent set size with which is close to the maximum. And it has been rigorously proved that it's not possible for polynomial time algorithm unless p equal to np. And if we further lower our expectation to see what if we don't consider the worst case, we only consider the average case, can we still find some near optimal solution? The answer is no. And the best polynomial classical algorithm can only find half of the size of the maximum independent set. And for quantum, the hardness are not very clear, but many attempts, such as the adiabatic algorithm, they are proved to have exponentially long time due to the exponentially small gap that we will show shortly. And this, and to just for this small demonstration, why is it so hard even in average case? It is because of the very rugged energy landscape of this problem. So the goal of the problem is to find the global minimum, but there are exponentially many local minimum on the energy landscape. So that once we run any local searches or any optimization algorithm, the algorithm will likely to be stuck at the exponentially many local minimum. So that's where the hardness comes from. And this picture would also be useful for our quantum algorithm because the energy here is essentially the same as the energy in the quantum devices. So the previous slide talking about the MS problem in a general setting, but here we come down to a specific subclass of that general graph, which is called unit disk graph. Why should we study it? Because the physical interactions, they are geometrically local, which means if we want to implement an edge that connects two very distant edges, very distant vertices, then it's generally very hard to do in physical systems. So instead, we consider this unit disk graph because by definition, the two vertices can have edge only if they are geometrically close to each other, which is essentially the physical constraint on the real experiments. So here is an example of a 2D lattice that can construct a unit disk graph. And what about solving maximum even set problem on this unit disk graph? It turns out that such graphs are much easier than general cases. And even in the worst cases, there are polynomial time approximation algorithm. And in the average case, many is very naive algorithm like greedy or linear programming and others can find near optimum for most cases. So here comes the problem. So we find a physically implementable set of graphs, but they are classically very easy. And similar problem has also been studied before, whereas in this book, they show that quantum algorithm can also find the exact MS with some classical post-processing. So the problem here is the classical post-processing is essentially the greedy algorithm. The greedy algorithm is very efficient to find the MS of such graphs. So if we only see the final outcome, we don't know whether the good result comes from the quantum optimization or simply comes from the classical greedy post-processing. So that's why we really need to find the classically hard instances, which means we want to exclude the classical contribution for finding the MS of such graph, so that we can see if quantum algorithm can really improve this result compared to classical algorithm. So problem is, how can we find such hard classical instances? So remember, most of the instances of unit disk graph, they are classically easy. So it's very hard to directly sample, like randomly choosing some geometry to find a classically hard instances. And luckily, we have some recent work, not by us, but by a group of people. They find that if they tune the geometry to be some specific lattice structure and tune the vacancy rate, which is the randomly drops some size from a fixed lattice structure, and within some parameter region, the classical sample from that region are classically hard with high probability. And this is one example from one example of such construction. So the lattice structure is just a triangular lattice with this hexagon shape, and we randomly drop sides from that. And here we drop two sides from that, and we find this kind of graph are hard for classical algorithm to find, polynomial algorithm to find its mass. So the reason is that there are some sites that can be easily chosen by classic optimization problem, but it's not contained in the true optimal result, which represent like a trap. So classical optimization algorithms, they can easily be trapped into this suboptimal result and cannot find the true optimal result. And for this, we sampled around like 10K such graphs for our use, so that all these graphs, they are hard for classical algorithm to find the exact maximum intimate sets. Okay, and with this preparation, we are kind of finding the truly classically hard problem, and then we want to implement the quantum algorithm to see whether there are any quantum improvements from that. Yeah, and before we introduce our new algorithm, we first briefly review the previously attempts on quantum advantage over such a problem. So the basic idea is called the variational quantum adiabatic algorithm. So this idea is based on the adiabatic evolution, where the initial Hamiltonian, it contains a very easy ground state, which is our zero state, and the final Hamiltonian, it contains a ground state that is exactly the maximum intimate set of that problem. And at the middle, we have the freedom to tune the interactions and Rabi frequencies and these detunings, so that we can find an optimal path that connect the initial ground state to final ground state. And the optimized result from their paper, it looks like this strip. So the tuning is initially at a very large negative value, then increasing to the very large positive value. And the Rabi frequency is sharply tuned on and then turn off. Yeah, something like this. And for this kind of evolution, there are exponentially small gaps during the at the middle of the evolution, which means if we really want to achieve adiabatic evolution, we require exponentially long time in order to do that, which makes the quantum algorithm in the ideal cases very inefficient. Yeah, but as finite averaging time, which is not exponentially long, how good is the quantum performance? And the answer is unclear, because we have noise and perturbations at the middle of the evolution. We also include the classical post-processing. So the true contribution from quantum algorithm is still unknown. Yeah, and similar to the previous algorithm, we also propose a new algorithm from a different perspective, but also based on adiabatic evolution. So the idea is that we first consider a fixed, a static Hamiltonian, which looks like this. So the construction is very simple. So whenever there is an edge, the state, then its energy will be raised by a constant value. So its ground state contains all possible intimate sets of a graph, and all non-intimate sets, they are automatically raised by some constant value. And we can do and we can prepare the initial state as a trivial solution, which is just our zero state, which is intimate set. And we want to evolve the trivial solution to non-trivial solution, which is MS. So I will not go into details about this, just briefly picture the ideas of how this driving is realized and how can this translated into the language of the Rydberg atom. So the basic idea is by global rotation of the Hamiltonian, so that the ground state degeneracy is always maintained. And so the evolution are effectively constrained at the ground state subspace alone. So we don't need to worry about the mixing from the non-independent set. And such global rotation will trigger a non-abelian geometrical phase inside the ground state subspace, and will effectively drive the trivial IS, which is the auxiliary state, to the independent set with maximum size. And this is effectively an adiabatic evolution in the ground state subspace. And by rotating frame transformation, this procedure can be exactly mapped into the Rydberg atom Hamiltonian, which are determined by these three parameters, and they can in the ideal case can be tuned by Rydberg atom platform. So the delta is the tuning, and phi is the phase of the laser, and omega is the gravity frequency. And in the ideal case, our protocol is essentially the same as these parameter changes. But in the real experiments, we have kind of restricted access to these parameters. For example, the phase is phi t it cannot be any continuous change of functions. So we have to set it as a fixed number. So and here the delta and the omega, we need also change it accordingly. And after some approximation, the result is very simple. So the delta is just a cosine function. Omega is just a sine function. And as a comparison, we compare our new protocol as to the previous protocol. So the previous one, the schedule is obtained by graph-dependent optimization, which is fix the initial and final point, and do optimization at the middle. But for our cases, we have a fixed schedule for any graph. And this saves a lot of shots number on real experiments, which means we don't really need the optimization. We don't need the optimization procedure. And the results shows for one graph instance looks like this. We compare the new algorithm with previous quantum algorithm and the classical algorithm. So the classical algorithm is plotted in this gray area. So we can find for such hard instances, the classical algorithm cannot find the true MS, but the two quantum algorithm can find some, and our algorithm performs the best. And we also show the performance with regard to the graph sizes. We can see a decreasing trend with one increase in the graph size. This is mainly due to the experimental restriction on the average time. So if we only have a constant average time, then as the graph increases, the complexity it will grow higher and higher. But the time we need for the adiabatic evolution will still increasing, but we only have a constant time at the real experiment. So it is expected that when the graph is too large, those two quantum algorithms will eventually fail if we cannot increase the evolution time. And this is a graph. This is a direct comparison of the two quantum algorithms. So we fix the graph to be the same geometry, and we compare the two quantum algorithms. One from the previous one and the one from our new algorithm. And we see for most graph instances, our new protocol performs much better. And I probably have to go through this, but I'll briefly describe why does our algorithm perform better than previous one? So so from first intuition is that the previous algorithm, it contains a very large effective interaction strength compared to the band gap of the two of the non-intimate set and the intimate set. So the blue area represents all the solutions, and the red area represents the non-solutions. The previous schedule, it has so strong interaction that the two bands can be intersecting. So once the area are intersecting, the noise or other fluctuations, it will mix the non-unit set into the evolving state. So that will give a bad result on the performance. In our cases, the interaction strength is fixed during the evolution, so that the non-even set and even set, they are very hard to mix. And this is from one intuition. And the second intuition is from considering the thermal reaction of during the evolution. So we can regard for the previous algorithm, we can regard the evolving state as something like this. So in the energy spectrum, the state is initialized at some high energy state, and the driving will gradually decreasing its energy. But there are thermal reaction happens at the middle of the spectrum, at the middle of the evolution. So the reaction, it will effectively effectively lower the energy of the evolving state, which means they can be trapped at the local minimum at an earlier time. Which means, for example, if you have a state which has some edges that are not occupied, and because of the occupying state has lower energy, the thermal fluctuation will relax the state at an earlier time to the local minimum. And in our cases, the energy spectrum is reversed. So the driving is effectively kind of increasing the energy of the evolving state. So the evolving state, it will evolve from low energy state to high energy state, but the thermal relaxation, it will be more likely to lower the state energy. So in this case, the thermal relaxation will not trap the state to the local minimum at some earlier time. So the effects from thermal relaxation is much lower from the new protocol. Okay, so I hope yes, I hope I have made it clear that our new protocol has some improvements over the previous quantum algorithm, and both of them have some improvements from classical algorithm. And in the future, it is valuable to implementing, for example, the graphs that have no geometrically constraint, which means any two vertex can have effect, and this is intrinsically classical hard instances. And if any breakthrough on this kind of hard graph, and that will be a big improvements. And also another possible optimization direction is on the evolution time. So here, because of the thermal fluctuations and other noises, we only have a constant evolution time, which makes this algorithm eventually fail at large graph sizes. But if we have something like a linearly increasing or quadratically increasing evolution time with some techniques from error mitigation or error corrections, we can possibly, for example, extend our result to larger graphs and truly classically hard graphs. And that concludes my talk, and thanks for listening.
We have some time for questions.
What kind of tools did you use to run these simulations?
So the classical simulations are very simple. Because we do classical simulation only for small graphs. So we do the exact diagonalization. So we exactly diagonalize the average exactly for comparison. And also for the problem itself, because it's a well-defined classical problem. So for MS, yeah. So for this kind of like problem, classical, although it's classically hard, but for small graph sizes like below 100, it can be very efficiently seen. So yeah.
A great talk. I was wondering if you've considered or thought about what would happen if you increase the frequency of your cosine and sine for omega and delta pulses.
Increasing the pulse strength?
No, not the amplitude, but like it had one period or half a period. If you increase the frequency of this.
What do you mean by?
So I guess for omega, you have like half a period, right?
Yes.
So if you have like you double the frequency of omega, so you kind of go up and down. And would that make a difference? Would that make it easier? Like from the picture that you had, it made sense that you might be able to do better. So I'm just wondering if you have a sense of that.
Yes, I actually tried this, but actually the performance gets worse because when you do this for multiple periods, the states actually get mixed severely by the noise and emissions during the evolution. So the and from the adiabatic intuition, so once you're increasing the evolving speed and more non-adiabatic effects will come in. So there will be mixture from non-independent set or small independent set something like this. So increasing the period itself, it doesn't increase the performance, but we can do it by slow it down. So yeah, but that will require longer average time, which is currently achievable on current machine.
May I ask a follow-up? So you did say something about being non-adiabatic, but to me, I don't know if I understand this correctly, but since you're changing delta to positive, isn't that very non-adiabatic because the initial state is the all zeros, all ground state?
Yes, so this is kind of like after some approximation, it remains adiabatic because if we consider the ground state subspace alone, then it's effectively evolved from a highest energy state to final highest energy state. And it's like inverse of adiabatic, but still by adiabatic theorem, if the evolution is sufficiently slow, the initial highest energy state will go to final highest energy state. Yeah, so that's still adiabatic, but with some